I think we are already live, so we can start with this webinar. So hello everybody, I am Roberto Lineros from IFIC, Université de Valencia and CSIC in Spain, and I'm going to be the host of this webinar of this series of the Latin American webinars of physics. So today we are going to have a very interesting talk because it's about leptogenesis that is closely related with the matter-antimatter asymmetry. That we know that the universe is formed of mostly matter. So, but before we talk, I want to tell you that if you want to make questions during this webinar to Diego Aristizábal, that is the speaker today, you can do it via here is the information, Google Q&A, and in Twitter with the hashtag LAWOP. And of course, if you want to contact us, you can simply write it in Twitter or in Gmail via email, simply. So, let's talk about the speaker. Today's speaker is Diego Aristizábal from the Université de Liège in Belgium, where he is an assistant professor in that institution. He obtained the PhD in physics in the University of Valencia, and after that he has done 2 postdocs, one in Frascati in Italy and another in Liège also. So the title of his talk today is Leptogenesis Beyond the Type 1 Seesaw, and I guess we can pass to Diego. Let me just unmute you. Diego. Oh, let's see if I cannot unmute. You have to unmute yourself. There is in the upper part a bar.
Like that, right?
Okay. So Diego, how are you? Yeah, I'm listening to you.
I'm good. Yeah, thank you. So first of all, thank you for the invitation. Yeah. Not only to you, but all the members of the crew, which are running this great idea of the Latin American webinars. Yeah, so
if you want, you can. All the people is listening to you now. You have the control of the webinar.
Okay, so I will start with my presentation now. So as we already said, I'm going to speak about leptogenesis beyond type 1 seesaw. I hope I can make my point clear. So basically, so let me see if I'm able to put this the way it should be. Okay, here it goes. Okay. Are you listening, Roberto?
Yes, I'm listening to you, and I can see your slides.
Yeah, but the point is that I'm having problems going to the full screen mode. Oh no, now it goes.
Now I can see it. Perfect.
Okay. Okay, so as Roberto said, I'm going to speak about leptogenesis beyond type 1 seesaw. So this talk is intended to be rather than something where I discuss particular results, a review talk. So the idea will be just to present, to give a motivation of these scenarios, which I call beyond type 1 seesaw. Try to explain what is the main idea behind going beyond this standard leptogenesis picture. So as soon as I review the basics about leptogenesis, which I think anyway is something useful, particularly for those which are not involved in this kind of physics, I will move on to more specific things. In particular, I will discuss. I won't be able to discuss all the 3 papers I want to deal with, but at least I aim at discussing this paper, which I wrote past year in collaboration from people in Brussels. This other one, which I wrote a few years ago in collaboration with people from the Joseph Stefan Institute in Ljubljana, Slovenia. And hopefully, as I said, if I have sufficient time, then I will discuss as well some results I got past year in collaboration with Avelino and people from Valencia, Professor Valle and Mariam Tortola as well. So let me go to my motivation. Of course, when you discuss this subject, from my point of view, the first thing you have to discuss is the current status of neutrino data. So partially, one of the motivations for this kind of scenarios where you try to address the baryon asymmetry puzzle of the universe by a mechanism named leptogenesis is related with the origin of neutrino masses. So this slide summarizes what we know about neutrinos nowadays. So people know, and all we know is that this oscillation parameters, neutrino oscillation parameters, the atmospheric scale and the solar scale, they are derived from global fits to neutrino oscillation data. So this neutrino oscillation data covers water, Cherenkov reactor, long baseline in radiochemical experiments. So the plots I have here, which I took from this reference, summarize what we nowadays know about the neutrino oscillation parameters. So the plots on top show the delta chi-square distribution for the solar, the atmospheric, and the reactor mixing angle, which 3 years ago it was proved experimentally that it doesn't have a vanishing value. So current fits to oscillation data actually favor a reactor mixing angle with a value of about 9 degrees. Now the plots here in this part of the slide correspond to the solar mass square, the atmospheric mass square, so mass square differences for the solar sector and the atmospheric sector. And this other one as well shows something that people have been discussing for a while, and is the fact that it might be that already data is hinting to a non-vanishing delta CP phase. So if you look to the best feed point value for the delta CP phase, then you realize that if this hint turns out to be true, the delta CP phase should have a value which amounts to 3 pi over 2. I don't have nothing else to add at that respect. I just want to point out that there are other ways, experimental ways, through which one can gain information about neutrino masses. These other ways are summarized here. So these are constraints coming from neutrino level beta decay, from which the best limits on this quantity are placed by Gerda, Exo, and Campbell and Sen, and tell us that this quantity should have a value which amounts to 0.2, basically. Then there are other sources from which one can constrain neutrino masses. Kinematic experiments which rely on kinematic endpoint measurements of the beta spectrum are determined by these two experiments, Mainz and Trosk, and tell us that neutrinos should have a mass below 2.2 eV. So of course when you compare the values you get from neutrino oscillation experiments, and you get as well from neutrino level beta decay, then you realize that these kinematic experiments are not that competitive, but certainly provide a complementary information of the full neutrino picture. And then cosmology as well provides limits on the sum of the 3 active neutrinos. So current values derived by, or provided by Planck, and also by baryon acoustic oscillation experiments, tell us that this quantity should be about below 0.23 eV. Now, the overall picture, when one looks to this experimental data, is that certainly neutrinos are massive, and moreover, we know that actually this year Nobel Prize went into that direction. Now, this is certainly a proof that we have to go beyond the standard model. We need new degrees of freedom. And basically, in my opinion, the whole goal of determining the origin of neutrino masses consists on pinning down the scale at which neutrinos are generated. Certainly, what we know is that we have to go beyond the standard model given this experimental information. Now, there's another intriguing data, and probably is not even relying on data, is actually something of the everyday life. So we know that there's more matter than antimatter. this quantity, the baryon asymmetry of the universe, has been measured precisely via cosmological experiments, astrophysical and cosmological experiments. So the basic idea is that in the cosmological standard model, the light element abundances, so I'm speaking about deuterium, helium-3, helium-4, so on and so forth. These abundances, they are a function of the baryon asymmetry of the universe. So as soon as you have information about these abundances, you can fit your cosmological model and determine the value for which you get consistently the values observed as a function of the baryon asymmetry of the universe. Now, it turns out that not only those measurements, but also measurements of the CMB provide information about the baryon asymmetry of the universe. Now, it turns out that the CMB spectrum, the shape of that spectrum, depends upon the value of the baryon asymmetry. So as soon as you have information about that shape, you can fit your model, and from that fit, you can derive as well a value for the baryon asymmetry of the universe. And actually, when you compare those values, so those values are shown here in this plot. The vertical orange strip is the range you get from measurements of light element abundances, while the vertical blue strip is the one you get from measurements of CMB. So when you look to this overlapping, because actually there's an overlap in here, certainly you can conclude that this is a great achievement of the standard cosmological picture, because measurements of light element abundances, or when you speak about light element abundances, you are speaking about BBN, which is an epoch in the early universe that completely differs from the epoch of radiation decoupling, which is in turn the epoch at which you can speak about CMB physics. So we are speaking about completely different physics, and on top of that, we are speaking about completely different eras during the evolution of the early universe. The fact that these two numbers match so precisely is, in my opinion, a great achievement of the cosmological standard model. Now, of course, given this information, the goal will be sticking to the standard model, investigating whether you can generate such an asymmetry. Well, people did that, and they realized that you cannot do that. So since this experimental information is pretty solid, is as well probably at the same footing that neutrino oscillation data. It is, in my opinion, a definitive proof that one has to go beyond the standard model. Now, of course, it will be nice, the goal will be to find a common framework where you can address such puzzles. So in principle, they are unrelated, but it turns out that when you stick to leptogenesis, these two puzzles turn out to be related. And here is how it works. So in a model-independent fashion, you can generate neutrino masses by the inclusion in the standard model Lagrangian of a dimension 5 effective operator, the so-called Weinberg operator. Now, this effective description is pretty powerful, and is pretty powerful because after electroweak symmetry breaking, you end up generating a matrix that has this form. This matrix already suffices to explain neutrino oscillation data. But of course, you want to get more. You want to pin down the region of the degrees of freedom which are inside this black box. This is basically the goal of investigating the region of neutrino masses. However, there's a feature, no matter the model you rely on, related with this operator. This operator is lepton number breaking. So you have lepton number violation. If you can assure, as soon as you put this operator at the Lagrangian level, that you have new sources of CP violation that you might probably even get from these couplings, and you can guarantee departure from thermal equilibrium, then in that case, you will necessarily end up generating an asymmetry in a lepton asymmetry in the early universe. Alone, that lepton asymmetry won't be capable of generating a baryon asymmetry. But it turns out that in the standard model, there are non-perturbative processes related with its Valerian reactions such that when you generate a lepton asymmetry, these sphalerons transfer part of that asymmetry into a baryon asymmetry. So the picture, the general picture, let's say the model independent quotation marks picture you get, is that you enforce your Lagrangian to involve Majoron and neutrino masses, and then when you couple that with sphaleron processes, you necessarily end up generating a non-vanishing baryon asymmetry. So in this kind of scenarios, leptogenesis scenarios, you necessarily end up relating two, in principle, unrelated puzzles, the region of the baryon asymmetry and the region of neutrino masses. And it's from that point of view that these scenarios are, in my opinion, and probably for many other people, appealing. Now, how does this work in type 1 seesaw? So basically, conventional wisdom is that neutrinos acquire masses via the type 1 seesaw, which means that if the Weinberg operator is generated via the exchange of heavy right-handed neutrinos, you can write a set of new interactions. So you have Yukawa reactions, Yukawa couplings, let's say. They will be reactions anyway, but I would like to call this, for the time being, Yukawa reactions. So you have these Yukawa reactions, and then you have Majoron and mass terms for the new objects here. Now, these Majoron and mass terms, they break lepton number necessarily. And the Yukawa couplings, you can prove, involve physical CP phases. So you have CP violation encoded in the Yukawa couplings, and you have lepton number violation encoded in turn in the Majoron and mass terms. Now, if you summarize what you learn from this Lagrangian, then you end up with the following picture. You have CP violation given by these couplings. You have lepton number violation given by these new terms. And then if you can guarantee that you can departure from thermal equilibrium, you will certainly end up generating a net non-vanishing lepton asymmetry. Now, the departure from thermal equilibrium is provided by the expansion of the universe. So this is a dynamics which is occurring in the early universe, being subject to fast expansion. The expansion provides the conditions that you need to satisfy so to generate a net lepton asymmetry. Now, this picture has been throughout analyzed in all possible ways, and certainly when you stick to the picture where you have a hierarchical right-handed neutrino spectrum, you can argue that what you have is the canonical picture for standard leptogenesis. Basically, the type 1 seesaw provides the framework for standard leptogenesis. Now, of course, given what I already pointed out, it will be worth wondering whether one can go beyond that picture. There's no reason why one cannot. But of course, everybody knows that the devil is in the details, so one has to go and check for other possibilities. Other possibilities are well motivated. So, in principle, one can argue that other realizations of the Weinberg operator do exist and are as motivated as the type 1 seesaw. So if I stick to type 3 and type 2 seesaw, let me explain why I mean by that. So in type 3 seesaw, rather than exchanging electroweak singlets, you exchange electroweak triplets, fermions as well. So the Weinberg operator you get through the exchange of these heavy fermion triplets. In type 2 seesaw instead, your recompletion is such that you generate the Weinberg operator via the exchange of heavy scalar triplets. Now, of course, you might wonder whether these kind of realizations are not motivated. Well, my point of view is that they are phenomenologically and theoretically motivated. Now, phenomenologically, I mean the following. So, The number of UV completions you can think about when you write the Weinberg operator is pretty large. So this has been recently proved. However, when you stick to these two realizations, type 3 and type 2, they are as simple as the type 1 seesaw. And you can argue that they are as simple as the type 1 seesaw because when you count the number of parameters that the type 3 seesaw involves, they amount to the same quantity that the type 1 seesaw has. When you go to the type 2 seesaw, you realize that even in that case, with a single triplet, you're able to generate neutrino masses, and the number of parameters you have at the Lagrangian level are smaller even than in the type 1 seesaw. So from that point of view, they are well motivated. Now, theoretically, one knows that the type 1 seesaw is certainly something that fits pretty well with the gut paradigm. So you invoke SO10, then you place your fermions in a 10-dimensional representation, and you know that out of that you always get right-handed neutrinos. You get electroweak singlets. Now, it will be, or it is worth wondering whether this is the case for type 3 and type 2 seesaw, and it turns out that it's like that. So if you stick to minimal SU5, so you know that fermions you place in the 5-dimensional representation, and also in the 10-dimensional representation. The Higgs sector and the minimal realization consist of a 5-dimensional representation, but if you want to, let's say, guarantee V-tau unification, you probably have to add a 45-dimensional representation. Now, gut breaking can be achieved in several ways, but the minimal way is certainly via the adjoint representation. And then, of course, in that setup, without lepton number violation, you cannot generate neutrino masses, and you want to do that. So imagine you want to construct an SU5 gut model capable of generating neutrino masses. So what do you get in that case? Well, there are several ways in which you can proceed. If you add a 24 fermion, then necessarily you will have right-handed neutrinos and also electroweak triplets. So basically, an SU5 enlarged with a 24-dimensional representation, fermionic of course, you always end up with a sort of interplay between type 1 and type 3 seesaw. If rather than relying on a 24 fermionic dimensional representation, you stick to a 15 scalar representation, then in that case, your SU5 model will generate neutrino masses via type 2. Now, the bottom line of this discussion in this slide is that type 2 and type 3 are as motivated, probably, or have involved sufficient motivations to wonder whether one can actually achieve, as it turns out to be in the type 1 seesaw, an explanation for neutrino masses and an explanation for the origin of the baryon asymmetry of the universe. So now let me go to leptogenesis in the type 3 seesaw. I think I have to speed up because I was told that timing is about 30 minutes. I basically am running out of time. Type 3 seesaw. Okay, what do I mean by that? So these are the kind of interactions you can think about in type 3 seesaw. So you have gauge processes, you have Yukawa processes, and of course you have Majoron mass terms, which break lepton number. Now, I won't go into the details of how you can generate neutrino masses in those scenarios, but anyway, I just want to mention that the mechanism through which you can generate neutrino masses with type 3 seesaw resembles what you do in type 1 seesaw. Now, the Yukawa couplings, as I said in the type 1 case, in this case turns out to be like that as well. They involve new CP biolatent phases. These new CP violating phases induce triplet CP violating decays. The amount of CP violation you can encode in this quantity, epsilon, which is just a CP asymmetry. And it turns out that when you impose neutrino data and you enforce your spectrum to be hierarchical, you can show that the CP asymmetry is bounded such that you have successful leptogenesis only when your triplets have masses above 10 to the 10 GeV. Now you can of course turn this argument around and saying that if you have a quasi-degenerate spectrum, the wave function piece that determines the CP asymmetry will be resonantly enhanced. And so in that case, it has been argued that probably you can have successful leptogenesis for order TeV triplets. Now, what are the processes you have to bear in mind in the heat bath? So remember that you have to guarantee lepton number violation. You have to guarantee CP violation, encoded in this case in the couplings. And then on top of that, you have to guarantee that your states departure from thermal equilibrium. Now, if you want to address that question, you have to account for different processes taking place in the heat bath. So this slide is rather technical, but I just want to point out that the relevant processes for a reliable calculation of the B minus L asymmetry are just the decay, inverse decay, of course, which provides the necessary washouts to generate sufficiently large B minus L asymmetry, and of course the corresponding one-loop corrections to these processes. One has to include as well something that at first sight seems like higher order processes. So I'm speaking about processes of this type, which correspond to S-channel exchange of triplets. The point is that in the absence of those states, you cannot end up with kinetic equations which are thermally well behaved. So you have to add them anyway. Now this process you can't forget about, because these processes, in particular these two, are suppressed by extra Yukawa couplings. However, the processes I have here you cannot neglect. So the guys I have here are guys that have non-trivial electroweak charges. They couple to gauge bosons in a non-trivial way, as shown here in this Feynman diagrams. And then you have to take them into account because these gauge processes are fast and they tend to thermalize the triplet distribution. Now, if you want to account for this thermalization, then you probably have to write kinetic equations. The kinetic equations I'm speaking about have this form. So you have a kinetic equation that accounts for the evolution of the triplet density, and of course you write a Boltzmann equation, a kinetic equation for the evolution of the B minus L charges and the different flavors, depending on whether you are or not in the flavor regime. Now, when you do that, you look to these equations, you realize that there's a competition basically between Yukawa-related processes and gauge processes. So this competition is somehow shown here in this plot. So here in this plot, I'm showing a couple of numerical examples for the behavior of the gauge reaction densities. So here with gauge reaction densities, I mean number of reactions per unit volume per unit time. Now, the blue line here corresponds to a gauge reaction density for a triplet mass of 10 to the 8 GeV. The red instead corresponds to the gauge reaction one obtains for a triplet mass of 10 to the 11 GeV. These other two curves correspond to these reaction densities, those driven by Yukawa couplings. Now one can realize, looking at this plot, I'm plotting here this reaction densities, by the way, normalized to this quantity as a function of set, where set is just the ratio between the triplet mass and the temperature. So if you want, it's like a dimensionless temperature parameter. So when you look to this expression, you realize that basically, depending on the relative size of the triplet mass and this parameter m tilde, which encodes the information about the Yukawa coupling, depending on the relative size of these two parameters, you end up either with a scenario where, in the case of the coupled gauge reactions, which means gauge reactions that go below this line, you have or not decoupled inverse decay as well. So these curves here, they refer to inverse decays. And for example, if I go to the triplet case, where the mass is fixed to 10 to the 11 GeV, then I realized that when this gauge reaction decouples, the inverse decay is still active. The inverse decay decouples later on. But if I go to the case where the triplet has a mass of 10 to the 8 GeV, then I realize that when gauge reactions become fast, when they decouple, the inverse decay is decoupled as well. So this behavior, this competition between gauge reactions and decays controlled by, or inverse decays controlled by Yukawa couplings, really plays a role in these scenarios. Now, before going into the actual results, I would like to mention the behavior of the lepton asymmetry in the unflavored case. Now, it turns out that you can analytically integrate the equations. You end up with a result of this type. Now, here you have three fundamental quantities. So you have the CP asymmetry in flavor I. You have this factor, which is the thermal distribution for the triplets. And then you have as well something which is the efficiency factor, which you have to determine via integration of kinetic equations. Now, this means that if you want to know what is the amount of B minus L you can generate, it is sufficient once you fix the CP asymmetry to calculate for the efficiency. So this plot here shows the efficiency as a function of the parameter m tilde for different values of the triplet mass, which I took to be 10 to the 10, 10 to the 11, and 10 to the 12 GeV. Now, there are two regions one can identify here. There's a region of a small m tilde, where one can realize that there's a strong dependence on the triplet mass. So the efficiency strongly depends upon the value of the triplet mass. And there's another region of large m tilde where you see that there's basically no dependence as soon as you start moving from a certain threshold on m tilde. So as soon as you start moving above that threshold from m tilde, the efficiency becomes independent upon the triplet mass. No matter the value you take for the triplet mass, you always get the same value. Now, this means that in those regions of parameter space, basically the gauge reactions are subdominant compared with those reactions driven by Yukawa couplings. Now, these observations allow us to split the parameter space of this model in two pieces. One piece which I like to call gauge region, and another piece which I like to call Yukawa region. They both obey to the following definition. Now, the gauge region, is a region where when gauge decoupling takes place, inverse decays are decoupled as well. And the Yukawa region is the other way around, in the sense that when gauge reactions are decoupled, the inverse decay is still active. Now, naively, even without doing any calculation, you expect that if you put flavor effects into the game, those effects should have an impact basically in the Yukawa region, because gauge reactions are flavor blind. So no matter the flavor configuration you take, you always will end up basically with the same amount. So no matter whether you have flavor effects or not, you will always basically end up with the same amount of B minus L asymmetry. Now here I have a sketch for what do we mean by lepton flavor effects. I will go through this slide rapidly, given that I'm running out of time now. But basically the point is the following. So there are three kinds of reactions you can think about in the standard mode, which are dependent upon lepton flavor. So these are the Yukawa couplings, of course. Now, if the reactions related with the Yukawa couplings are not fast, which means their rate processes, their rate is smaller than the expansion rate, then of course the lepton doublets that propagate in the space of time are just superposition of the different flavors, with the composition determined by these factors that tell you which amount of tau, mu, and electron flavor you have in that particular lepton doublet. Now, if you have a standard mode related reaction, which is lepton flavor sensitive, and it turns out to be fast. Fast here means faster than the expansion of the universe. Then you might end up breaking the coherence of that quantum state. It turns out that people investigated that like about 10 years ago, and basically the point is that you can divide the temperature regimes in different windows depending on whether certain reactions are or not fast compared with the expansion rate of the universe. Now, these are the windows you can think about. I won't go through them. I just want to point out that for the results I'm going to present in the next slide, I will stick to this window. The window where both the bottom Yukawa coupling and the tau Yukawa coupling are in thermal equilibrium. Now, when you include flavor effects, of course, you have to specify a given point in parameter space, and for that aim, the flavor composition of your lepton doublets you can specify using flavor projectors. So for this particular two examples I have here, I have fixed my flavor projectors according to these values. There's no motivation behind that, rather than just highlighting the main physical features of the behavior of the B-L asymmetry in the presence of flavor effects and in the absence of flavor effects. So the results are divided in the two regions I already pointed out, gauge region and Yukawa region. And well, in this plot, where I'm basically showing the efficiency magnified by a factor 10 to the 4 as a function of set for these two parameters fixed according to 10 to the 12 for the triplet mass, and 2 times 10 to the minus 4 for the effective neutrino mass, if you wanted to call it that way. So basically the parameter that is determined by the Yukawa couplings. So in this plot, I'm displaying two results. One for the flavor regime, which corresponds to the red dotted line, and one for the unflavored regime, which corresponds to the blue curve. Now, as expected, in the gauge region, you don't have basically any enhancement due to flavor effects. And as I already pointed out, the reason is that in that region, gauge reactions, they do play a role. And since these gauge reactions, they do play a role and they are flavor blind, there's no reason why you should expect in that particular region of parameter space to have striking effects due to the inclusion of lepton flavor. If you move instead to the Yukawa region, then you realize that the picture completely changes. So for the same point, for this point, but changing the m tilde parameter from 10 to the minus 4 to 10 to the minus 2, remember that moving from one region to another for a fixed triplet mass is determined just by the change of m tilde. You can realize that in that case, when you move deep inside the Yukawa region, the enhancement you get on the resulting efficiency, or if you wish, on the B-L asymmetry is striking. So you start having enhancements of 2 orders of magnitude. So certainly, once you realize that you can split the parameter space region of this kind of models in 2 pieces, you know that whenever you want to have flavor effects into the game, you want to have sizable flavor effects, you necessarily have to move to the Yukawa region. Well, I have here other result, which basically shows the same picture that I already ended up in the previous slide. So I think I rather skip this one. And I would like to ask Roberto whether I can keep going or you believe it is worth stopping here.
I think that it would be nice if you can continue a little bit more.
Oh, sure. Okay. Okay. So I think I can be done in 8 minutes or so.
Okay.
And I apologize for such a long time.
Yeah.
Okay. So let me move on to the leptogenesis in type 2 scenarios. Now, the idea here is rather simple. doesn't differ too much from what you get in type 3 seesaw in certain aspects. However, there's a major difference. Regarding neutrino mass generation, it is well known that you can well account for neutrino masses in the presence of a single triplet. So a single triplet suffices to generate neutrino masses in agreement with experimental measurements. That's it. Now, if you want, in addition to that, to address the baryon asymmetry puzzle, then you have to go beyond that minimal picture. Going beyond that minimal picture is not unique. You can do that in several ways. So you can, for example, argue that rather than having a single triplet, you have more than one. You have whatever number you wish. Or you can think as well of having a sort of hybrid scenario where you don't only have triplets, but you have the neutrinos. This will be actually the kind of scenarios you will end up with if you stick to SU5 with fermionic representations lying in the 24-dimensional representation, fermionic, of course. Now, let me just say why this idea doesn't work if you just have a single triplet. Now, if I have just a single triplet, I can only think about a one-loop correction to the corresponding decay, something of this sort. Now, if you look to this plot, to this Feynman diagram, then you realize that this diagram is one particle reducible. You can cut this diagram here. So in principle, it looks like a correction to a decay, but it's not a correction to a decay. It's just the self-energy of the triplet. So of course, in that case, you don't have any contribution to any one-loop contribution to the triplet decay into leptons. Now, if you move into the picture where you allow for additional degrees of freedom, you add, for example, extra triplets, then you can think about two possible one-loop corrections to the decay. So you can have something of this sort, or you can have something of this type. Now, these two pieces, they differ, and they differ in a non-negligible way in the following sense. So when you look to the Lagrangian, you have something which is lepton number violating here. So in addition to the Yukawa couplings and to the gauge processes, which are determined by kinetic terms, you have a trilinear scalar coupling. This trilinear scalar coupling breaks lepton number. So when you look to this kind of processes, you know that necessarily they will involve lepton number violation. This one instead involves only Yukawa couplings, and these Yukawa couplings are lepton number conserving. So these kind of corrections are lepton number conserving, while this one is lepton number violating. As I already said, you can as well, if you better like type 1C, so you probably can stick to pictures where you have interplay between type 1 and type 2, and then in that case you will have corrections to this decay determined by this kind of processes. Now let me focus on pure type 2 contributions, meaning only scalar triplets. Now in that case, as I said, you have two contributions to the CP violating phase. You have one which is flavor and lepton number violating, and you have another which is not sensible to the fact that you have or not lepton number violation. Now this piece, not caring about lepton number violation, enables purely flavor leptogenesis. And this is something that these people and myself and collaborators pointed out past year. What do I mean by purely flavor leptogenesis? Well, in this kind of scenarios, well, it turns out that the CP asymmetry is lepton number conserving, meaning that the different pieces that determine the CP asymmetry, they break lepton flavor, but they don't break lepton number. So when you sum over lepton flavors, your total CP asymmetry vanishes. Something that has been noted long ago, probably 20 years ago or so. Then, of course, you have to wonder, if you have a CP lepton conserving quantity, how come you can end up with a B minus cell asymmetry? Well, you can write your, in the two-flavor regime, you can write your CP asymmetry in this way. If you write in this way, and you recall that the B minus cell asymmetry can be written as the CP violating asymmetry times the efficiency, then you will have two contributions. One, which will be the efficiency related with the tau flavor, and another one related with the efficiency in the A flavor. Now, the only way through which you can get a non-vanishing B minus cell asymmetry is if your efficiencies don't match. And if you want to guarantee that, you necessarily have to guarantee in turn that your washouts are lepton number violating. Okay, so this is the point. In Taiwan seesaw, you find as well this kind of behavior. So in Taiwan seesaw, you have two contributions to the CP violating phase. The lepton number violating one goes as the ratio of Mn1 to 2 and 3, while the lepton conserving one goes as that ratio to the second power, which means that if you stick to the conventional standardable leptogenesis picture, where you have hierarchical neutrinos, this piece is always subdominant. It might be relevant, and it turns out to be relevant actually, in scenarios where you have a slightly broken lepton number. Scenarios with slightly broken lepton number necessarily involve quasi-degenerate spectra. And if you have quasi-degenerate spectra, there's no reason why this term should be more relevant than this other. Now, in type 2, you have the same behavior, but the parameter dependence is completely different. So the lepton number violating piece depends upon, if you wish, on the branching ratio of the triplet going to final state leptons. Okay, basically it depends upon Yukawa couplings. The lepton number conserving piece instead depends upon the branching ratio of triplet going to scalars, or if you wish, to the trilinear scalar couplings. This means that whenever you go to scenarios where the branching ratio of the triplet going to Higgses is much more smaller than the branching ratio of the triplet going to leptons, you always end up with dominance of this piece. And therefore, you can think about constructing in that way pure flavored leptogenesis schemes. Now, of course, if you want to do that, again, you have to do the exercise of rethinking what are the relevant asymmetries you have in the thermal bath. This is a bit tricky in this case because the triplet is not a self-conjugate state, as it turns out to be, for example, in the type 1 case. So you have to account for a triplet asymmetry, which is sourced by the B minus cell asymmetry. Now you have as well, and this is a key point, you have as well an asymmetry in Higgses, because this guy, the triplet, not only decays to leptons, but also to Higgs doublets. Now the point, or the question is, how can you treat the asymmetry you generate in Higgs degrees of freedom? Now there are three possible reactions you can consider. You can consider reactions which are much more slow than the expansion of the universe. So those reactions are so slow that at the time where you calculate the asymmetry you are generating, they basically haven't happened. So you can't forget about them. Then you have reactions which are fast compared with the expansion rate. These reactions you can resume through chemical equilibrium conditions. And then you have the reactions that you have to treat via kinetic equations. Now, in this etap, the B minus cell asymmetry you track using Boltzmann equations, while the Higgs asymmetry, being shared by all the other degrees of freedom of the standard model, which are fast, should be resumed via chemical equilibrium conditions. Now, bearing that in mind, you have to consider all the possible processes. This I won't discuss. Just want to point out that you have any way to consider gauge reactions, because these guys have non-trivial charges under SU2 cross U1. And then, if you do that, you end up with a very nice picture for purely flavored leptogenesis, which works in this way. This is a sketch of how it works. When we tackled that problem past year, what we did was properly integrating the kinetic equations and treating all the possible effects, including, as I said, chemical equilibration. But here, with this sketch, it's pretty simple to understand how the picture for PFL within type 2 seesaw works. So as I said, you need washouts to be lepton number conserving, but when you, violating. But when you look to this expression at first sight, it seems like this quantity is lepton number conserving because it's driven by these branching ratios which are controlled by Yukawa couplings which don't break lepton number. Now the point is the following. In the initial stage, just in the initial stage, you generate through the source term the same amount of B minus cell asymmetry along the tau and the A direction. That asymmetry that you generate sources the triplet asymmetry, but it sources the triplet asymmetry weighted by a factor that has a flavor structure. And so it weights the different B minus cell asymmetries in different ways and necessarily generates a non-vanishing triplet asymmetry. Now, once you have a non-vanishing triplet asymmetry in the bath, you, of course, will have more triplets than anti-triplets, or vice versa. If in the heat bath you have more triplets than anti-triplets, well, of course, you will end up with more leptons than anti-leptons. So the lepton number violation you need in washouts is basically provided via that mechanism. So this triplet asymmetry here you have provides somehow the lepton number sources you need so to guarantee that your washouts are lepton number violated. The sketch is like as I draw here. So at the beginning you have same amounts of B minus cell asymmetries in the tau and the A direction. Then in the stage where you still don't have any lepton number violation in the heat bath, these two amounts you have source the triplet, which due to this weighting flavor dependent factor end up sourcing the washouts, and at the end you end up with a mismatch between the B minus cell asymmetry in tau flavor and an A flavor, and of course with an asymmetry in the Higgs as well. So this is a mechanism which relies entirely on a triplet asymmetric plasma that enables having, in the presence of delta E equals 0 decays, a non-vanishing B minus cell asymmetry. This is just a result, just to have fun, of the behavior of the parameter space of this setup, which shows the maximum B minus cell symmetry you can get in this kind of PFL scenarios. These PFL scenarios based on a triplet density which is asymmetric in the heat bath as a function of this R parameter, which is defined in this way and which encodes the information about the possible flavor structures you can conceive. The value you want to generate amounts to 10 to the minus 11. So you can see that you can, for different values of this R parameter, you can always generate sufficiently large B minus cell asymmetry. Even if you impose neutrino data, as we did, so the green points are for the normal spectrum, the red points are for the inverted spectrum. So even in that case, you see that you can always generate sufficiently large B minus cell asymmetry. So you end up with a very nice picture where you generate the B minus cell asymmetry, you spline neutrino masses, and you do that through lepton conserving triplet decays, which at first sight seems, quotation marks, counterintuitive. Now I want to close just by mentioning other non-standard variations, given that I won't have time to discuss the last part of my talk. One can think about interplays between type 1 and type 3 seesaws. These are things that I did some time ago with these collaborators of mine. So if you conceive scenarios where you have certain small hierarchy between the right-handed neutrinos and the electroweak triplets, then they both will participate in the generation of the B- cell asymmetry, and of course, in those cases, depending on the regions of parameter space you deal with, you can end up with sizable enhancements of the B- cell asymmetry as well. Then you can conceive as well the possibility of generating dynamically the right-handed neutrino masses, in which case, if you rely on global lepton number breaking, then you will end up with new degrees of freedom, including a Majoron. The presence of these new scalars can potentially affect the way in which leptogenesis takes place, even in the type 1 seesaw. This is something we investigated past year. And then, of course, you can stick to other pictures, to other realizations of the Weinberg operator, one-loop to loop realizations. This was done about 10 years ago by Thomas Hamby and some of his collaborators. It turns out the bottom line of this analysis is that if within your realization you have states that have non-trivial SU2 cross U1 quantum numbers, then these guys will couple to gauge bosons, and then this coupling to gauge bosons will produce thermalizations down to low temperatures, which in turn implies lower bounds on the masses of these new states. Then the new masses of these new states, the bounds, can be in principle used, provided you can produce these guys at LEC to rule out some of these scenarios for leptogenesis. Well, that's it. These are my conclusions. I let you read them. I think this is sufficient for now. Actually, it took me almost an hour. Yeah, so I hope some of you are still tuned. So that's it.
Okay, thank you very much, Diego. It was a very nice talk. I mean, the topic is very interesting. So now we can, let me just adjust some stuff here in the Hangout. Okay, so now we can start with the questions. So before to start with those, I just remember to the public, the ones that are following the streaming, that you can make questions via the Google Plus Q&A system and in Twitter with the hashtag LAWOP. So let's start first with the question that for the public that we have here in the Hangout. Maybe someone want to start? Okay.
Sorry, do I stop sharing my screen?
You have to stop to, yeah.
Okay.
So yeah, you can, let's see your face also, to see if you get scared with the questions or not.
I might get scared, yeah.
So very good. So let's start with the question. I have a couple of questions. One, I mean, before the other people start with questions, if the LHC will be able to reach some of these questions, I mean, some of these models.
Yeah.
So this is the perspective in the future.
Yeah. So this is something that has been discussed recently, actually. So somebody you have just close to your room, Martin Hirsch, he wrote a paper past year where they pointed out that the discovery of lepton number violating interactions at the LEC will basically not rule out completely, but will introduce certain tension in scenarios for standard leptogenesis. In general, for mechanisms where you rely on the production of the B- LSE through lepton number violating interactions at the high scale. So in that case, the main point is that no matter how large the asymmetry you generate at high scales, the washouts implied by those reactions that you are observing at LEC will wipe out whatever you generated. Now, of course, there is a loophole in that case, because it might be that you generate the asymmetry in certain flavor, okay? And it might be that at the LEC, you observe certain flavor structure. Now, if you observe certain flavor structure, it might be that you can still store certain amount of lepton asymmetry in that given flavor. But certainly this puts some constraints on these leptogenesis scenarios, which rely on high-scale mechanisms. So this is one of the things that it will be nice to observe at LEC. I mean, per se, of course, it would be great to discover lepton number violating interactions at the LEC, or whatever we can discover. But certainly the observation of lepton number violating interactions at the LEC will probably speaking, rule out this idea of generating the baryon asymmetry via a violation of lepton number at high scales, up to the loopholes I pointed out. And then you also asked about other ways. Well, these other ways rely on a different on a different way of thinking. So as I said, when you have states that have SU2 cross U1 non-trivial charges, these guys couple to gauge bosons. If they are very light, they are thermalized basically down below the temperature at which its values decouple. If you are generating an asymmetry, you need the aid of its values to reconvert that quantity into a baryon asymmetry. So you have to guarantee that your states don't decouple before its valerian decoupling. And this implies a bound on the masses of those states. Typically, at least for type 2 and type 3, the number you get is about 2.3, 2.5 TeV. Okay. Now, I don't know whether the LEC has capability for producing such states. But if the LEC turns out to produce a state which has a mass below 2.5 TeV, let's say a scalar triplet or a fermion triplet, then in that case, let's say you find a state which has a mass of 1 TeV. In that case, you can guarantee that that state alone cannot be entirely responsible for the baryon asymmetry of the universe. So the observation of a light state at LEC will basically, up to loopholes, will rule out the possibility of generating the asymmetry via either type 1, type 2, or type 3 seesaw.
Okay, so in that sense, it means that one possibility is just to have this flavor leptogenesis that you were presenting.
Yeah, in my opinion, my understanding of this problem is that you cannot avoid that. You cannot avoid having flavor effects provided your standard mole lepton flavor dependent reactions are faster than the expansion rate. This is determined by the temperature at which leptogenesis takes place. So as soon as you go below that temperature, basically as soon as you go below 10 to the 13 GeV, you know that your setup or your analysis should rely on flavor degrees of freedom. So it's not, in my opinion, my understanding, it's not up to you. You have to include them because this is a physical process which implies basically quantum decoherence of a state that before the reaction was fast was completely quantum coherent.
Thank you. So maybe someone else has a question from the, otherwise we continue with the questions that are already in the Q&A system. So, okay, now we have another question from Andres Felipe Rivera Romero. So he's asking to you, what about the three-body decays, like alternative to generate the lepton asymmetry? In the Fukujita-Yanjida classic model, it works. Is it not necessary in your case? I mean, yeah.
What he's asking about three-body decays?
Yes. How they?
He cannot turn on the microphone. Probably it will be better if we can.
No, because he's just following the streaming, so he only can write questions. Maybe he can complement the question now. If
yeah, probably.
come back to this question later, maybe he can write.
So he's speaking about three-body decays in which scenario?
In the model of Fukujita-Yangida.
So he's thinking about red-handed neutrinos three-body decays.
Yeah, maybe.
Well, I don't see how this three-body decays can compete with a two-body decay. And actually, I mean, if I properly understand his question, so the decay one has is a heavy guy, a guy that has mass at the gut scale, decaying to leptons and Higgses. So I cannot think about a three-body process in that case.
Yeah, maybe.
If you can explain what kind of three-body process he's speaking about, probably I can give an answer.
Yes, maybe we can ask to Felipe, to Andrés, Felipe to complement a little bit his question. Maybe we can pass to another one. So there is another question here from Jose Valle. I mean, I guess it's related with the first one, with the first question of all.
Oh, he was attending my seminar.
Yeah, he was looking to seminar.
Oh, so he's around?
I guess he's in his office.
Okay, tell Professor Valde that it's an honor for me that he's attending my seminar. Yeah.
Virtually attending. So if the lepton number violation is seen at LHC, then you roll out the leptogenesis picture. Yeah, right? Martin's paper is quoting.
Yeah. So basically, this is what I said. Up to loopholes, you rule out the leptogenesis picture in the sense that if you observe the states, the lepton number violating states who have masses, let's say at 1 TeV, you cannot say nothing below 1 TeV. So if you can think about a mechanism that generates the asymmetry and the size that has to be generated below 1 TeV, then you cannot say nothing, because at that point washouts don't play any role. So if you observe a state, a lepton number violating state at 1 TeV, then of course you can exclude all possible mechanisms from that point above. As I said, up to loopholes, and the loophole basically is storing the symmetry along different flavors. So basically you have to make a definitive claim, in my opinion, you have to determine the flavor structure of your new lepton number violating physics. For example, if your lepton flavor structure is such that is democratic in all flavors, then you are done. You know that all these mechanisms are ruled out. But if it turns out that this new physics is such that it couples more to leptons, while to taus, while basically doesn't couple to electrons, there's no reason why your washout in electrons should wash out completely the asymmetry you generated at the gut scale, if you wish.
Mm-hmm. Yeah, I understand the point. It's very interesting, in fact, because it goes beyond the standard scenario. I mean, all the flavors are the same and everything. So
yeah, but I think making a definitive claim, I mean, the claim is sufficiently strong, but a definitive claim, like saying you rule out leptogenesis occurring above certain critical energy scale, the scale at which you produce the state at LEC, requires determine as well the full structure, the full flavor structure of your new physics.
Okay, so I guess this question is answered. So maybe, okay, let's go with another question. This is related more with, okay, if it is still possible to have leptogenesis when you generate the neutrinos masses at one loop processes, like you have a kind of conserved charge that forbid to neutrinos to acquire masses at tree level and only loop.
Who is asking that?
Mm-hmm?
Who is asking that?
Me.
Ah, okay. Thank you. Okay. Well, as I said, depends. Depends. It's pretty mole dependent. So the answer is somehow mole dependent. Now, if your state entering into your UV completion, the UV completion that accounts for your one loop realization or the two loop realization, you have is a standard mole singlet, then you, I would say, certainly can do it. Now, if your state does not have, or does have actually SU2 cross U1 quantum numbers, then in that case, whether you can or not generate a sufficiently large B minus L asymmetry will depend upon the mass of this new state. Again, using the argument I gave before, it depends that value, the value for that mass, depends upon the temperature at which spherules decouple. Now, with current measurements, with the value we have for the Higgs mass, you can calculate the temperature at which spherules decouple. That temperature is about 140 GeV. Okay, so you have to guarantee that your states generate sufficiently large lepton asymmetry above that value. Now, if your new state, the state you have in the loop, or in your 1 or 2 or whatever loop you wish to have, is such that is kept in thermal equilibrium close by to this 140 GeV or even below, then you know that this mechanism doesn't work. As I said, this basically implies the other way around argument implies that you can place a bound on the state below which you are not able to address the baryon asymmetry puzzle of the universe through leptogenesis in that scheme. Okay.
Yes. Perfect. So it's still, yeah. So, I don't know, more questions? Otherwise, we have the last one here in the queue of questions. So this one is more or less inspired with dark matter, in the sense if these scenarios also are compatible with, for instance, extra hidden or dark symmetries like U1 B minus L minus dark that correspond to the dark sector.
Yeah.
Kind of inspired by asymmetric dark matter or the opposite. Asymmetric dark matter model inspired by leptogenesis.
Who's asking that?
Me also.
So you were the only one attending to my seminar.
They're thinking, person. They're thinking.
Yeah. Okay. So when you speak about these scenarios, you are including type 1 seesaw, or you are only speaking about type 1 or type 2, or in general? What you're speaking about in general? In general. Well, whether you can, I mean, the main point is the following, is that there are three things you have to satisfy. You have to satisfy CP violation, lepton number violation, and departure from thermal equilibrium. As soon as you can guarantee that, you can embed your scheme in a larger scheme where you can do much more things. So for example, you can think about scenarios of loop-induced neutrino masses where the same symmetry that enables having the neutrino mass generated at a certain level stabilizes one of the degrees of freedom you have there. So that state, in principle, like it happens in the scotogenic mole, that state will play the role of dark matter. And then, as it turns out to be in the scotogenic mole as well, you have the right-handed neutrinos, out of which you can generate the lepton asymmetry. So the scotogenic mole is, from that point of view, a benchmark mole with which you can argue that you can always construct scenarios where you have leptogenesis, dark matter, and neutrino masses in a single shot.
Very interesting. Yeah. So
if you find an appealing model, let me know. We can work it out.
Yeah, for sure. So let me see, just in Twitter, if we have some questions. No, it seems that we don't have in Twitter. I don't know the rest of the people in the Hangout if they want to address the last question.
There was a question by this person, which
yes, I don't know if he can add an extra comment on his question to make it more easy. I guess for the stuff that was written, I guess he was thinking in a model in which you only have 3 body decays, and for some reason 2 body decays are suppressed.
Yeah, okay, you can think about scenarios of that type, but certainly the Fukuyama-Yanagida scenario is not you have 3 body decays. You can think about scenarios, for example, you can, now it comes to my mind, that you can think about the C-mole. So in the C-mole, you can construct, you can draw 3 body decays which generate the lepton asymmetry. And you can show that in that case, as well, you can generate sufficiently large lepton asymmetry. So this is something that was done by Thomahan B. Probably, if not in the late 90s, probably about 2002, 2003, or even before. So he studied that problem. So of course you can think about scenarios where you have 3 body decays. What will be the difference? Well, if you have a 3 body decay and you compare that with the case where you have a 2 body decay, reaching the condition of being decoupled, of reaching the condition of being out of thermal equilibrium is different, because of course in a 3 body decay you have an extra suppression factor determined by phase space. So if you wish, you can think of this 3 body decay as a 2 body decay where you rescale your Yukawa couplings in such a way that your Yukawa couplings are smaller. This means that basically by a 2 body decay, your states will decouple before than in the 2 body decay case, because it's basically like if you have something which is 2 body decay with a coupling which is 10 to the -1 and 2 body decay with a coupling which is 10 to the -4. If you stick to this language that people like to use, weak and strong washout, this means that moving from the 2 body decay to the 3 body decay is equivalent to moving, quotation marks, from the weak washout, from the strong washout regime to the weak washout regime. That's the only difference. So your states are less strongly coupled to leptons than they will be in the presence of just 2 body decays. That is the only difference. And this statement, in my opinion, is completely mole independent. Doesn't depend upon the mole you are dealing with.
Okay. Yeah, very. In fact, this is a topic that is worth to know. Leptogenesis and what is happening in the early universe. So let's see. No, there is no more question here in Twitter. And last chance for the people if they want to ask. If not, I guess we can start to close this session. So we acknowledge Diego for this very interesting webinar. And for the people that is looking this video already in YouTube, you can make comments and leave it here, and we are gonna make this comment to arrive to Diego in order to, if you want to contact him or start to collaborate with him. So for what I'm concerned, so we can stop this webinar here. I'm just gonna present. This is the ending of the webinar, and these are the people that are behind the team. So I hope you enjoyed this webinar, and we are gonna see you in the next one. That is, in principle, it's gonna be like in 2 more weeks. So have a good day and see you soon.